The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, I'm Lynn Trong with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the U.S. Department of Energy Solar Decathlon. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You can either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we'll eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right should have your telephone number and PIN. Panelists, we ask that you please mute your audio device while you are not presenting. If you have any technical difficulties with the webinar, you can contact the GoToWebinar's help desk for assistance. If you would like to ask a question today, please use the questions pane to type in your question. If you are having difficulty viewing the materials through the portal, today's webinar is being recorded and the recording will be available. And now for today's presentation. Our webinar today is Solar Decathlon. Ingersoll Rand presents HVAC systems for zero energy ready. Our speakers today are Rachel Romero, project leader and energy engineer at the National Renewable Energy Laboratory and design challenge manager. And we have speakers from one of our two 2019 design challenge host sponsors, Ingersoll Rand. With that, I'd like to welcome Rachel to start today's presentation.
Thank you, Lynn, and welcome everyone today to the webinar. It is my great pleasure to introduce Matt Biesterveld and Wayne Kraft, who will be presenting today. As Lynn said, they are one of our host sponsors, and I believe they have a lot of great content to share with you all today. So, presenting first is Wayne Kraft. Wayne is a research engineer in the Advanced Solutions Group for the Residential HVAC and Supply Business Unit. As a research engineer, he leads projects developing new solutions for residential HVAC products in the areas of airflow systems, heat exchangers, controls, and HVAC systems. Wayne graduated from Texas A&M University with a Bachelor of Science degree in Mechanical Engineering, and he continued his education at Texas A&M University, receiving both a Master of Science and a Doctor of Philosophy in Mechanical Engineering, specializing in thermal and fluid sciences. And then Matt will be presenting a little later in our webinar. Matt Biesterveld is the leader of the Customer Direct Service Group and product manager of Trace 3D Plus at Trane. He is responsible for leading a team of engineers in product development, support, and training for Trane's suite of engineering, design, and analysis software tools. Matt graduated from the University of Wisconsin-Platteville with a Bachelor of Science degree in Mechanical Engineering and has completed the Trane Graduate Training Program. He is a certified ASHRAE Building Energy Modeling Professional, BEMP, a certified energy manager, CEM, and is currently on the board of directors for the International Building Performance Simulation Association, ABIPSA USA. Wayne?
Thank you. So our topic for today is going to be HVAC systems for zero energy ready buildings. And we're going to divide this into two different parts. This first part, which I'm going to cover, is going to be on HVAC equipment, just overview and how to select it. And then the second part we're going to do, Matt is going to take care of, is going to be on building energy modeling. So this is just really an agenda for what we're going to cover in this first part. And a lot of what I'm trying to do in this content is really give you a general overview of HVAC systems, some of the technologies involved in them, and some of the different design considerations that you should take in selecting equipment. And so you see we're going to cover just a general HVAC overview. We're going to go through different equipment types. We're going to talk about how to drive efficiency through selecting your equipment. We also want to talk about comfort, because it's not just about efficient systems, but how we provide comfort in the home and the building. And that includes humidity control. We'll also talk about ventilation, how we bring fresh air into a structure. And then we'll close with talking about how to size and select equipment. So on this first part here, I wanted to talk about what is a typical system. And I would say probably the most common technology that you'll see for a heating or cooling system is going to be a vapor compression cycle. So this is what we have schematically on the far left. And I don't want to go into too much detail, but I thought it would be useful just to talk about the basics of how it works in the context that you're going to see as we go through the rest of the discussion today. And so where I kind of want to start is a vapor compression cycle really is taking advantage of using refrigerant to transport heat in or out of a building. And one of the ways it does that efficiently is refrigerants can exist both in a vapor phase and a liquid phase, and it's taken advantage of that phase change to do that heating or cooling very efficiently. And what I want to start with is if you look on the far left of that diagram where it says expansion device, we're going to start there. So as refrigerant enters the evaporator, we are using an expansion device to take it to a very low pressure and temperature. And the goal, if this is a cooling system, is that we want that refrigerant to be colder than the air in the building. And that way we can cool that air and absorb the heat from the building and take it away. And so we're doing that by evaporating the liquid and two-phase refrigerant until it's completely a vapor or a gas. And once it leaves the evaporator, we want to find some way to reject it outside of the structure. And one thing we have to consider is, for instance, is cooling. Well, it's hot outside, it's warm outside. So we want to reject this to an environment that's already hot. And so how do we do that? And that's where a compressor comes in. Is that we're going to take that refrigerant, which is a vapor and it's cold, and we're going to compress it to a very high pressure and a high temperature, such that it's now hotter than the outdoor temperature. And now we can actually reject that heat that we just absorbed from inside the building to the outdoor environment. And so that's the job of the condenser. So after the compressor, the refrigerant is going to go through the condenser. It's going to be still a vapor, but it's going to be hot, and it's going to be warmer than what it is outside, and it's going to reject it, condensing it back into a liquid form. Okay, and at that point, we can start the cycle over again. And one of the really nice parts about this cycle, and that we take advantage of in the HVAC industry, is that it doesn't just provide cooling, is that there's an opportunity, depending on the equipment you select, to have what we call a heat pump, where you can reverse or interchange the functions of the evaporator and the condenser, and now you can provide heating to the building in addition to just doing cooling. So now that we've kind of established those basics, I want to go towards the middle screen, the middle diagram we have here, where we say split systems. So what is a split system? Well, when you locate this evaporator and this condenser in split systems, they're physically separated and they're connected by a refrigerant line. So you can see the labels for the evaporator on the indoor equipment where we're cooling the indoor air, and typically that might be an air handler. And on the outdoor equipment, that has the condenser heat exchanger where we're rejecting it to the outside environment, and that could be a heat pump. And to contrast that, we can go look at what's on the far right of the screen is a packaged product. And so the technology is the same. If we would go back to that vapor compression cycle and look at that, the same technology is in that packaged product, but instead it's all in one enclosure. And typically that would be placed outside the building, and it'd be connected to the building via air ducts. So now that we understand what a typical HVAC system looks like, I wanted to go into more detail of some of the different ways of using those type of technologies that you're going to see if you look at different solutions that are going to be differentiated. And so the first thing I want to start with was methods of transferring heat to or away from a building. So we said before, like in this example with cooling, the evaporator, it cooled the air, it absorbed the heat from the building, but now we want to take it away outside of the structure, right? And so the first example, which is probably the most common, typically in residential or multifamily applications, is what we call air sourced. So it's the example I just gave on the previous slide, where we're rejecting all that heat to the air outside. The next one, if you look in the middle, is an example that we would call ground sourced, or it could also be water sourced. And really the difference there is, instead of rejecting to the air, we're going to reject to piping that's either underground, or it could be, for instance, like in a large water supply, or in some cases people have abundance of water. It may even be open loop with water. They're pumping it out of a well and then they're basically discharging it into another well. That would be ground sourced or water sourced heat pumps. One of the advantages of this you're going to see is that you're no longer tied to the particular weather conditions, how cold it is outside or how hot it is outside, in terms of how the equipment behaves, because you're now rejecting to the ground or water, which is much more stable. The last example I have on the slide on the far right is what we would call evaporative cooling. And I decided to include this one. It's not as general as the previous two we just discussed, but it is unique in that in dry climates you have an additional choice where you can use evaporative cooling. What it's trying to do is basically use the process of moving air across basically a sheet of water. And when you do that, you're going to evaporate some of that water into the air and basically humidify that air, but you're also going to get a cooling effect. And so when you're in dry climates, that's something you might see sometimes as kind of a niche solution that they can uniquely take care of. So we just talked about how we are going to transfer heat in or out of the building. What about how do we transfer the cooling or heating capacity throughout the building? So how we can deliver it to the different spaces or zones to provide comfort. And so what I have on the left here is probably the most typical solution, which is using air ducts. And so you have a centrally located air handler that you can see with the AH. It is cooling, so basically you're cooling the air there centrally, and then you're distributing it throughout the building or the structure via a plenum, branch ducts, and then supply registers. You can contrast that with what's on the right, which would be a ductless solution, which would, instead of having ducts, it would actually have refrigerant pipes or water pipes from the outdoor unit. And instead of having one centrally located most of the time piece of indoor equipment, you could actually have one or multiple. And so basically the refrigerant or water in the pipes is what's transporting the cooling or heating capacity throughout the structure. And the actual work of cooling the air or heating the air is done in the actual zone with a dedicated piece of equipment. Some other words you might hear, and I kind of have them on the bottom, that might be of interest are, particularly if you're looking at commercial products, you'll see this terminology, and it describes this a bit, is you'll see things like variable air volume. That's kind of another name for zoning, but it's a way of distributing capacity to different zones through varying the airflow, right? The middle one is variable refrigerant flow, so that's kind of self-explanatory. It would be more like we talked about in the ductless example, where you're using refrigerant flow to deliver capacity to each of the specific zones. And the last one would be variable water flow. So you'll see those terminology when you look at different systems, particularly in the commercial space. So now that we've introduced, how we reject heat from the building, and how do we transfer heat or cooling capacity within the building, I wanted to introduce some terminology that if you go out and you investigate different systems and you see maybe perhaps the specification for the capacity or the efficiency of the system, that you have some kind of background into some of the terminology that'll be used and can interpret that. So I'm just going to work my way down as we go through here. The first one is capacity. So this is how much heating or how much cooling can you provide with that piece of equipment. The typical units you would see on that is going to be BTU per hour. And sometimes you might also see the word ton. And what a ton is basically the rate of heat transfer to melt 1 ton of ice in a 24-hour period, right? And so you'll see both those terminologies when you see equipment described. Now, in terms of efficiency, all these other metrics you see below here are different ways to talk about efficiency. The first one is EER, and that is energy efficiency ratio. And that is the ratio of I'm going to give an example for cooling here, but cooling capacity divided by input power. Now, what's unique about the energy efficiency ratio is that the units are not the same for the cooling capacity and the input power. So there are units to it, and it's specific to basically the HVAC industry. If we go down to the next one, COP, which is coefficient of performance, it's the same ratio. We're talking about capacity divided by input power, but the difference is now is the units are the same for both. So both could be in BT per hour, they both could be in watts, but basically it's more like what you would see as a textbook definition of efficiency. So the one thing I would say as we talk about EER and COP is that they're usually described at one set of conditions, okay? But the reality is the way HVAC equipment works is you're applying it every day at a different type of conditions. The weather is changing, what you're controlling the indoor temperatures to is different. And so since all that variability is there in how we use it, we need other metrics to additionally understand efficiency. And that's where these last two come in. So if we talk about SEER, that is seasonal energy efficiency ratio, that's just a way that through our testing procedure and the way we calculate efficiency that we can account for the fact that this piece of equipment is going to operate under varying conditions throughout the year. HSPF, which is heating seasonal performance factor, is really the same thing. It's just for heating. So now I want to get into the actual equipment that you might find. And so the first topic I want to do is ducted equipment. And this is probably the most common solution that you would find for particularly the residential multifamily market. I've got some examples here on the screen if we go left to right. The first one is heat pump and air handler. So it's kind of like those first graphics I showed on the early slides. So that can do heating and cooling. The next one would be an air conditioner. So the refrigeration cycle only does cooling, but heating would come from a furnace, and you would have an air conditioning coil, which is your evaporator that you would have inside the building. And the one on the far right is what we call a packaged product. So we saw that earlier, and that could be any variation of what you see on the left. So some of the advantages we have with that kind of product is that ducted equipment tends to have a lower first cost. It tends to be pretty simple to operate and troubleshoot. It's kind of the advantage that you have one outdoor unit with one indoor unit. You also can have the flexibility if you want it, and we see this a lot, particularly like two-story homes, where you can have a unique set of equipment or unique system on each zone. So like on a first level of a building, you could have one piece of equipment cooling or heating it, and on the second level of building you could have another unique one. So you can condition the building uniquely in that way. Also, because they use a duct system, you can distribute the capacity throughout the structure directly into the spaces that you want to condition and achieve uniform comfort throughout the building. Another important one is that if we talk about ventilation and bringing in fresh air to the structure, it's fairly straightforward to integrate mechanical ventilation into this type of equipment because you have the duct system available for you to distribute it. Some of the disadvantages. So we don't see this as much maybe the residential multifamily, but probably more in commercial products where you have many zones, is if you have a lot of individual pieces of equipment like this ducted equipment, you're going to size each of those to the peak load of each zone. So if you total all that up, it's possible that if you had a central piece of equipment, it could actually be smaller because not all the peaks occur at the same time. So that's kind of one disadvantage. You might actually install a little bit more capacity with ducted equipment, especially split system ducted equipment. The other one is we're distributing that capacity throughout the house using air ducts. Well, we're having to do work to do that, right? So that requires fan power. And so there is a cost to distributing that capacity throughout the building. Another important one to consider are losses. So since we have ducts, depending on where they're located, there can be losses. And so the example I would give, probably if you think about many like existing homes, ducts tend to be in attics or crawl spaces. And many times that is not inside where the insulation is for the building envelope. It's actually in the outside environment where it's really hot or it's really cold. And so that can represent a loss. And so that is a disadvantage unless you bring the ducts into the conditioned space, which is a more common building practice we're seeing in new construction now for efficiency. And the final one I have there is that you have all this equipment and you have ducts, you have to accommodate it. So if you're doing the architecture of the building, you're doing the layout, it's something that you have to accommodate all those mechanical systems. The next one is ductless. So I have 3 versions on here we'll go through quickly. The top one is what we would call a mini split. So it's a lot like the split system we saw before, but without ducts. But you are connecting the outdoor unit and the indoor unit via a refrigerant line, but there's only one of each. And that indoor unit is controlled in the one location, that one room that you're trying to condition the space with. So it's not necessarily a whole house solution or a whole building solution, but it allows you to do one particular space. The next variation I'm going to do is, if you go down to the left, is a multi-split. And so that handles, well, I have more than one space I want to condition. Well, how do I do that? Well, with this example, you can see you still have one outdoor unit, but you have many indoor units. The restriction here is that you can see the way I drew this is there's a refrigerant line going to each one uniquely. And so you are constrained on how many indoor units you can have, and the expansion that we talked about before the evaporator, it's actually occurring at the outdoor unit. And so there are some more challenges with efficiency there that you wouldn't have if you didn't do that. The last one I want to show is commonly you hear the word VRF, but it means variable refrigerant flow. We talked about that earlier. And it's much like that multi-split, except for now, instead of having individual refrigerant lines to every indoor unit, you have one set of refrigerant lines that is shared across all the indoor units. And so one advantage of that is basically it's more modular, and it's a little bit simpler to set up, but it's also more complicated. So the advantages in general for this type of equipment is there are smaller space requirements. You don't have all the mechanical equipment and ducts that you have to accommodate. And since you don't have ducts, you're avoiding those losses. So you don't really have that decision of whether you want to pull them into the conditioned space or not to eliminate the loss. And they tend to have some flexibility and modularity. You can see with the multi-split and the VRF, you can add units on, you can take them off, you can have different kinds of units. There's some flexibility with that. The disadvantage, I would say, is that it tends to have a higher cost associated with it than ducted equipment. Another challenge that I've seen, particularly in some studies that have been done, is if in particular this happens, I would say, like in a residential home. So if you have several bedrooms and individually they're not large enough load to have multiple pieces of indoor equipment, and so you really need one ductless indoor equipment to provide capacity to all those individual rooms, it can be hard to do that with ductless products. So you start getting into, like, you have to layer on other solutions to basically provide capacity to each of those rooms, since the indoor equipment is going to have to be in a common area to them. So that may be like transfer fans, transfer grills. In some cases, I've even seen where they actually put duct system in, but it's just circulating air. So there's just challenges that have to be dealt with to do that. The other one that happens, a lot of times this is more of a concern probably in commercial buildings, is, well, how do you introduce ventilation air if you don't have a duct system? How do I get it to all the spaces that I have people when I do something that's ductless? So these are the last 2 pieces of equipment that I wanted to talk about before we move on. So the first one we see on the far left is, again, we're revisiting the ground source and water source heat pumps. And so a common name you might see for these is geothermal heat pumps. The advantage of these, and I alluded to this a little bit earlier, is that you can take this kind of heat pump into colder climates. If you have an air source heat pump, there are some limitations, as you go to colder and colder climates, it's more difficult to extract heat from that cold outdoor environment and do it efficiently and provide the capacity that you want to have. So you end up with supplemental heating solutions often. With ground source or water source heat pumps, because you're not dealing with the outside air and the fact that it's cold, you're dealing with the ground or a water source that is more invariant to the different weather conditions. You can extend heat pump operation into much colder climates, and that's a good thing. They also tend to have higher efficiencies because of that. They aren't dealing with the variability of the outdoor environment and those temperatures, and they're dealing with something that's more consistent and mild in temperature in terms of the ground. Some of the disadvantages, it tends to be higher first cost. So you don't just have the equipment now, you have this ground loop that you have to accommodate, and often it's much like drilling a well. They have to drill a large hole in the ground. There are many of them, depending on the size of the system, and there's a cost of doing that and putting the heat exchangers in the ground, and you wouldn't have that in other types of equipment. You need the space for that ground installation. That's another challenge that has to be overcome. And some of the performance, if you're looking at a spec sheet for it, that is representative, but one of the challenges is when you go actually install it at a particular site is your heat exchanger is the ground. So depending on what soil type is there, what it's like, you will have some variability in performance. The last one I want to talk about is hydronic or radiant heating. So this really means using water as your heat source. So one of the advantages of this is that really where you get your hot water is flexible. So there's many different ways you could do that, whether that's a boiler, it's a solar thermal array, it could be a heat pump even. Any of these things could create hot water, and that's a good thing. And so it's flexible about how you get that source of heat. And then the next part is what's kind of unique about it is when you do radiant heating, one of the things is when we feel cold, we're not just reacting to temperature, we're also reacting to the temperature of not just the air, but the surfaces around us, okay? And that's what's really nice about radiant heating that's unique, is that you're actually warming some of those surfaces, and in some ways that can feel more comfortable when it's really cold. In terms of disadvantages, in terms of the residential market, I was really describing heating. You don't really see radiant cooling, and so you would have to have a different cooling system. One of the challenges, whether it's residential, commercial, whatever it is, if you try to do radiant cooling, is how do you deal with moisture? If you're taking surfaces of the building and you're cooling it down in the space, you could actually get moisture to condense on the surfaces. So you have to have another system that dehumidifies the space, taking care of that latent capacity so that you don't have that problem. So we've gone through all these different equipment types. What we wanted to do was give a little bit of calibration to what you might find if you looked it up in terms of efficiency levels. So the first one on the top left, this would be just a typical ducted air source heat pump. And so we talked about seasonal cooling efficiency. So we have here is like 22 SEER. In terms of the seasonal heating efficiency, we have 12 HSPF. If you move over to the ductless side of that, you're going to see you can find products that actually go a bit higher. You can see 38 SEER, 15 HSPF. If you go look at the multi-split, which is a little more flexible in terms of meeting multiple zones within the house, you see something more similar to the ducted air source equipment. The ductless has 24 SEER, 10.5 HSPF. And then what's a little bit different as we go to the bottom right with the ground source and water source heat pumps is they don't necessarily always have a seasonal efficiency metric because they aren't responding to all these varying outdoor conditions. They really just give it in terms of a single efficiency at one condition. And so you see here 40 ER and COP of 8. So we've just gone through introducing all these equipment types and the technologies involved. And so I just want to quickly just give some suggestions of ways that you can maximize your efficiency in the building by selecting your HVAC equipment. And so the first one I want to talk about is if you start looking out there for HVAC equipment, particularly for split systems, you're going to see products that they're going to say they have variable speed compressors. And what that really means is they can provide variable capacity. So the compressor can speed up, slow down, and you can modulate the capacity higher or lower depending on the needs of the structure at any given time. What's great about that is you're not turning the equipment on and off all the time. When you turn equipment on and off, there's a loss associated with that. So you get to avoid that with these variable capacity systems. So that's something to look out for. You also get the added benefit of improved comfort. So when you have something that's just turning on and off, it's harder to maintain a constant temperature within a space. But when you have something that you can actually modulate the capacity you're providing at any given time, you can have much better temperature control. The next one on there is, everything at this point, we've been talking a lot about the equipment and the efficiency of the equipment, how it behaves. But we talked about how we distribute capacity within the home, and there's certainly can be done well or not, right? And there's losses associated with that. And so if you're trying to maximize efficiency, if you're using an air duct system, you would want to put those ducts in the conditioned space. So you don't want it outside the building envelope in an attic outside the insulation. You actually want to pull it inside the insulation so that any type of leaks or anything it's interacting with is actually inside the building envelope and it's no longer a loss. And I think you'll start to see that more if you start looking at energy code. It's really driving new construction in that direction to try to avoid the losses that you see in much older homes. In terms of controls, there's things you can do for energy efficiency there. You can have schedules, occupancy detection, remote access. The last one I've listed is called smart recovery. It's basically, you'll see that terminology a lot, but it's basically when you have, let's say the space is not occupied for a while and then somebody does come in and you need to start providing comfort. How do you return back to your comfort set point? How do you do that? And smart recovery is basically the idea that you want to do that in an efficient way. The next one I have is thermal storage. You don't tend to see this much in residential applications, but you do see it quite a bit in commercial. But it's just the idea, either in the design of the building or even integrated with the HVAC system. You could choose to have, for instance, like ice storage and cooling, where you run the equipment, overnight or at times when it's cool, and the equipment is very efficient, so that you don't have to run it later when it's hot outside and it's not as efficient, right? So that's one way to just kind of displace the demand to a more efficient time. And the last one I have there is economizers. And so economizers is the idea that when the outside temperature is actually something that would be comfortable and you need some cooling in the structure, is that you could actually bring in that outside air directly and provide comfort without turning on the cooling system. You see that quite a bit in commercial buildings. So the next part I wanted to do is on comfort. Everything we talked about now has been efficiency. How do we do efficient equipment? But the purpose of this equipment is to provide comfort to people, right? And the particular issue I wanted to talk about was humidity. So when we talk later about doing load calculations and how we size equipment, one of the things we do want to consider is not just the hottest day of the year or the coolest day of the year, but we also want to consider periods of the year where our moisture loads are going to dominate, and we might have issues if we didn't look at it, right? And so you want to make sure that even in those periods when we don't have a lot of heating or cooling, but there's a lot of moisture load, we're selecting equipment that can still maintain comfort in the building. On the bottom, we just have a list basically of some of the common solutions for that. One of the things is you do want a thermostat which controls the equipment that can at least sense humidity and have algorithms to basically deal with that. Okay, and then one of the things you can do is when you select indoor equipment, equipment that has variable speed indoor blowers. And what I mean by that is that it can increase or decrease airflow dynamically, can give some ability for humidity control when you combine it with the right thermostat control. And then the final one I have is if you are in a very severe climate, something that's very humid, you may actually need something that's a supplemental that can do dehumidification and maintain the humidity in the structure. And that might be something like a whole house dehumidifier, a ventilation dehumidifier. So there are refrigeration systems on their own that are dedicated to removing moisture from the building. This is really a continuation of the previous slide, but this actually comes from a design guide we do where we try to help people understand in terms of humidity, what they need to think about in terms of solutions. And it doesn't mean this is going to work for every building, but at least kind of helps guide them to what they need to think about. So this came from a study that was originally done actually through ASHRAE, which is an industry organization that does a lot of research for us. And then we've updated it as part of work that we were interested in, where we were trying to identify solutions that in different climates that are somewhat humid, that you can keep the humidity largely under 60% RH. And 60% RH is important because that's when, if you stay above that for long periods of time, you have the likelihood for mold. And so you can kind of see on the far right, we are looking at climates that, well, they have some humidity, but it's not really what we would call a severe location. And probably more typical high efficient equipment would be sufficient to meet those humidity needs. If you look at the middle one, and so this would be an example like a Houston, where you're starting to get pretty humid. and just typical, equipment may not be satisfactory, is you have to start getting some of that we said before, like you need the indoor equipment that allows us to vary indoor airflow. We need thermostat controls that can sense humidity and have algorithms to control the system in a way that could minimize humidity. And then as you get to really severe climates like southern Florida, at some point you're going to have to start thinking about, well, I need a dedicated system that also can help remove humidity. And that was, like we talked about before, is having dehumidifiers that you could add on top of these other solutions that we just talked about for Houston and these other climates. So that was comfort and humidity. But what about keeping the environment healthy? And so what we mean by that is making sure we have sufficient fresh air inside the structure. And one of the common ways of talking about that is indoor air quality, IAQ. So if you were to look, there are requirements on this. ASHRAE, which is that industry organization I was talking about, does have requirements for both the residential and commercial marketplace in terms of what is required for ventilation, introducing fresh air into a building to maintain a healthy environment. And one of the concerns when this has kind of been a newer, I would say, set of requirements. I mean, they've been doing this probably for the last 10 years, but you wouldn't have seen a lot of that before then. Is that, well, if I'm introducing all this air from outside, isn't that hot or isn't that cold? Isn't that increasing the load on the building? Isn't it adding humidity to the building? And so there was a lot of concerns that, yes, it's good that you're bringing fresh air in, but is there anything bad that we're doing? And there's been a number of studies that ASHRAE has done on this, and I think the conclusion has been is that the benefit of having fresh air far outweighs any concerns that would be on the increased load applied to the structure and the energy usage. And the last one I have is that this is actually really important for net zero ready homes because the construction, the building envelope is so good, it's so tight that you don't have this natural ventilation occurring in basically the leaks and cracks in the home. The older homes, that's what we have. We don't realize it, but we have ventilation. It's just happening naturally because there's basically all these small holes in the house, right? But in these newer homes that are very efficient, we're doing a really good job of sealing them up for efficiency. So then if we want it to be healthy for fresh air, we have to actually design it in. So we have to provide some kind of mechanical ventilation solution to bring that fresh air in purposefully. So we're nearing the end here. So just to finish up the indoor air quality options, there's three types. On the far left, we have what we call exhaust. So in exhaust, we are exhausting our stale air that's inside the building out, and we're bringing our freshened air in basically through those cracks that do exist in the building. And that might be harder to do in, like I said, in some of these very efficient houses because they're sealed so well. One of the things we don't like about that is it can be challenging for combustion appliances, and we don't have as much freedom to filter it. It's being brought in through cracks in the houses. We don't have a filter. The middle one is supply ventilation. So here we're actually pushing fresh air into the house, and basically it's exhausting through all the cracks in the building. It's one of the things that's nice is that you can filter that air, and so you can keep it clean. Disadvantage is you do want to distribute it, so you may need some ductwork, or you need to actually tie it into the existing ductwork for the primary HVAC system. And then the one on the right is what we would call balanced ventilation. So with supply ventilation, your house tends to be, or the structure tends to be have a positive pressure relative to outside. With balanced pressures, balanced ventilation tends to be neutral. So we have actually two fans on it, one to push air into the building and another one to exhaust air from the building, and it's meant to do it in a balanced way. One of the nice things about this is you're going to see a note on there that says ERV or HRV, but basically it's ERV is the energy recovery ventilator, but the idea is basically, since you have two fans and you have two air streams that are local to each other, is that you can exchange thermal energy between them or even moisture between them. So if you think of like you're in a really cold climate and you've already paid to heat the building, if you're just pushing all this air out, that's a loss. But if you use something like an ERV, you can actually take some of that heat that was in that exhausted air and actually use it to exchange with the cold air you're bringing in and raise its temperature so that you're not losing all that energy. So I'm just about at the end, and the last thing I kind of have here is how do I select a system? And mentioned this a little bit about load calculations, but it's very important that when you're designing a building and you're selecting an HVAC system, that you know that you're selecting the right system that can meet the needs of that structure. You need requirements, and a load calculation is a way to generate those requirements, selecting the HVAC system. And the way you do that typically is that you identify a design day, okay? And that design day will be one for cooling, there'll be one for heating, and it tends to represent kind of an extreme in the population of outdoor conditions that structure is going to see at its geography. So for cooling, you can see I have a note here. It's like 1% outdoor temperature. The heating tends to be the 99th percentile outdoor temperature. And what you're accounting for when you do these load calculations, it really is an energy analysis. You're accounting for the solar gains, the infiltration loads, which is basically that air and moisture that's leaking into the building in one way or another. The internal loads, people are loads, right? Even the appliances that we're using. Conduction loads through the actual structure. And then we said ventilation. If you have ventilation, you're certainly bringing in the outside into the structure. So it's doing an energy balance, but at a particular set of conditions. So one set of conditions for cooling and one set of conditions for heating. And it's giving you an idea of what's happening at that peak loading condition so that you can pick equipment that's sized appropriately to meet comfort at that time. One of the things that we do have to be careful with is not just to look at the temperature comfort, which is what we would call sensible load, but also at moisture, like we said before. We need to understand our latent load, which is basically how much moisture do we need to remove from the building at different conditions for people to be comfortable, but also for the building to be healthy and we don't have mold and other things that we don't want happening. One thing we do have to keep in mind that this really is just a calculation meant to give you one day. What does this peak load on one day look like? It's to help you size and select your equipment appropriately, but it's not the same thing as building energy modeling. That's a much bigger picture that gives you an idea of how your equipment is going to perform over the whole year, how much energy it's going to perform over the year, and what that comfort is going to be over the year. So I wanted to leave you with some references that would be in the webinar. A lot of when I was reviewing the material for this, I looked up a lot and I was trying to read some more just to familiarize. And one of the best ones I would say that resource out there, and I think even with libraries you should have access to this, are ASHRAE handbooks. I mean, they're basically textbooks for HVAC systems. And it's not just the design of them or the fundamentals, it's also talking about how to apply them. It's talking about the specific types of equipment and how you use them. And so I just listed a few chapters, but the reality is they're a great resource and there's much more in there that I have described even here. The bottom one, and I think I had some graphics earlier on the slides, you may have seen them, but I didn't mention it, but ACA manuals. So ACA is the Air Conditioning Contractors of America, and they have manuals. So when we talk about load calculation and talk about applying equipment, they have manuals that give you specifications for how to do that load calculation correctly, and they have guidelines for how do I apply equipment in a robust way that's going to deliver comfort or perform properly. And so they're also a great resource for information for how would you do basic select systems and apply them appropriately. So last thing I have before I turn this over are just some of what I consider to be the key takeaways from the talk today. The first one is that to have an efficient building, I mean, HVAC certainly, it is one of the primary energy consumers within a building, but it's not just about picking the HVAC equipment, it's also about how you apply it. What decisions do you make when you apply that equipment? The second one is that, yes, efficiency is really important, but the purpose of the HVAC equipment, and we can't forget that, is to provide a healthy and comfortable environment. And so to do that, we do need to consider indoor air quality and ventilation. We also need to talk about indoor humidity and what solutions we might need. I focused a lot earlier on removing humidity and dehumidification, but the reality is in cold climates, sometimes you need humidifiers because it gets too dry. And the last one is you need to consider, well, how are you going to distribute this capacity throughout the building and provide comfort? Because it's not about just having this system and you say, oh, it's on this building. It's also how you provide it to those spaces. How do you deliver it to every one of those spaces and make each one of those comfortable, that as people are going through the building and working in each space, that is doing what you want it to do. The final one we have on there are load calculations. So I can't stress that enough. Like you really can't pick the right solution unless you define the requirements for what that solution needs to be by doing a load calculation on the structure that you're designing. So I know that's a lot that I just did, but I think that's everything for this first part. So at this point, I'm going to turn over the rest of the presentation to Matt, and he's going to talk about building energy modeling and analysis.
Thanks, Wayne. Okay, so just waiting for control to take over here.
Did you get a prompt?
I did not get a prompt. Waiting for it here. Last time I did.
Because it's showing that it's with you, but let me see if I can grab it back and do it again.
Okay. Still got nothing.
Okay, just grabbed it back and I turned it back over to you.
Okay. Let's see here. Unfortunately, I am not getting the prompt and I am not able to take control.
Okay, let me flip it to someone else. Wayne, I'm gonna send it back to you.
Okay.
And then Matt, I'm going to give it a couple seconds and then bring it back to you.
Okay.
Do you see Wayne's slide?
Yes, I do.
Okay. Do you see the go-to slide right now?
I just see the Solar Decathlon Design Challenge white screen.
Yes, and does it say presenter? Does it have your name?
No, it says Wayne is the presenter.
It
says Matt.
Technical challenges.
Yes. Hold on one second, and let me see why you're not getting the prompt. And Matt, I'm going to flip it back over to you.
Okay. Yeah, it still says Wayne at the top as presenter.
Wayne, what do you see? And Rachel?
My screen updates as Matt as the presenter.
Correct, mine too.
Oh boy,
Wayne,
oh boy.
Matt, do you want to refresh possibly? And I'll pull it back to Wayne. Let me pull it back to Wayne while you, that way you can open and close your application. Just your screen.
Yeah, I'll do that quick. Yep.
Okay, hold on.
Okay.
Hey, Matt, when you're ready, I'll flip it back to you.
Yep.
You ready?
It's still refreshing. Hold on.
And I do have a few, thank you to the participants who've been kind enough to verify that they see that Matt, you got switched to Matt. Thank you.
Okay, give it a try. I refreshed it. I don't know if that worked or not. Boy, it did not. I still see a white screen with it saying it's connected to. I'm going to disconnect and come back on real quick.
Okay, go ahead and do that. Thank you everyone for your patience as we work through this technical issue.
Lynn, do you want to ask a few questions?
Yeah, if
Sure.
anybody has, yeah.
Yeah, sure. So while we're waiting, just a few questions that have come in. We'll go ahead and answer those, ask those. Rachel or Wayne, so with Ingersoll Rand as a sponsor of Solar Decathlon, is it okay for individual teams to also have them as an industry partner?
So this is Rachel, your competition manager. Ingersoll Rand and Train are a host sponsor, but you are more than welcome to reach out to them or others within the company to be your unique collegiate institution and team's industry partner in the competition. Wayne presented some really great resources, and they have provided some resources as well on the groups.io under sponsors. So definitely check that out as a great resource.
Great. And this is a related question. So our teams who are participating, are they required to use Train products and resources in their projects?
You are not required to use Train products and resources in your project, but they are offering some great resources to use, including what I believe Matt is about to talk about, which is Train Trace 3D. The offering for that is currently on the groups.io, and then I think Matt will talk more about that here shortly as well. Good questions.
Great, thank you, Rachel. And as we are waiting for Matt to log back in, and this is related to some of the technologies that you were talking about, Wayne. Is it something, you talked about the benefits and the pros and cons and things like that, but could you just touch on the cost impact? Like, is one more beneficial and than another from a cost perspective?
Well, that's actually kind of a complicated answer. So I was trying to be fairly general with costs because as you go from equipment manufacturer to equipment manufacturer, they are going to vary. But also the installation costs. I mean, those, as you go to different geographies, they do vary quite a bit. And that could really influence the decisions. So I was intentionally kind of being a little bit vague with that and not really giving specific costs because I don't want to give you something inaccurate, right? I was just really trying to give you something more directional, to be honest. And so, you know, I'm kind of comfortable with what I said before. You know, in terms of ducted equipment, that does tend to be the split system ducted equipment tends to be probably the most lower cost option. You probably go from there to probably ductless systems, and then probably from there you would go to probably like the ground source heat pumps. But again, it's kind of relative. It also depends on the installation costs, which can vary greatly by geography. Some of those can be incentivized. Like one of the things that happens with ground source heat pumps is sometimes there's federal subsidies, state subsidies, and that can make a large impact in a particular region where it may be viable with those subsidies, but without it, it's not as attractive to people, right? And so I'm sorry I'm giving a kind of an indirect answer here, but it's because it's a bit of a hard one to answer directly because it can vary so much, depending on where you're located.
Great, thank you so much, Wayne. And just as a reminder, I know that a few of the attendees have raised their hand, and unfortunately, due to the number of people on the call, please go ahead and submit your question through the questions pane because we won't be able to unmute any of the participants at this time. So I'll ask you another question, Wayne, as we're waiting. You talked a little bit about the balancing between after the technology is talking about the comfort and that type of thing. What is your advice in terms of balancing out comfort for all the various projects that are involved in the solar decathlon, residential, commercial, whether it's an office building, a school, a home? Do you have any general guidance on how teams should gauge and factor in that comfort level for occupants?
So I didn't introduce it in here, but if for instance, in the ASHRAE Fundamentals Handbook, there is a section on comfort, and it'd probably be pretty useful, I mean, for people in general just to understand better. But there is something they call like the comfort envelope, and it's not as specific to the residential environment. I would say that in the residential environment, multifamily, comfort really is what the person says it is. You know, if they go to their thermostat and they set a temperature, that's their comfort. You know, I mean, it's individualized. When you get into commercial buildings, there really isn't individualized comfort anymore. You can't, right? I mean, you have a population of people. And so it's more looking at population metrics. And so that's kind of what you see with like the comfort envelope. It basically gives you a range of temperatures and humidity levels that in group, like as a group, a general group of people would be comfortable in, right? It doesn't mean every individual is the most comfortable at each of those points, but if you kind of stay within that envelope, then generally people will be happy. Now, I think that's one of the things, you know, talk about like how do you identify whether you're really providing a comfortable building. That is where someone like when Matt presents the building energy modeling tools are really uniquely qualified to address that, because when we do a load calculation, we are really just doing a calculation at one point in time for sites and equipment. And that, it's valuable, but it doesn't really tell you a whole lot more than that. And where the building energy modeling tools come in is they're predictive. You're going to put the layout of your building in there. You're going to actually model your equipment that you're choosing as a solution, and essentially you can try it out, right? And it's as good as basically the model you create. And so it's going to analyze what your equipment and building is going to do as a whole. Basically, you know, most of the time it's usually hourly analysis, so you're going hour by hour throughout the year, and you can get an idea of whether you think your equipment solution is capable of providing comfort within the space and what kind of energy usage is doing, you know, to achieve that. Some of the other things, you know, from just a practical standpoint is, you know, I did mention, you know, there are challenges, you know, even with designing duct systems and providing comfort. You know, that's where ACCA comes in. They have practical guidelines on how you should size your ducts, select your ducts, how you should place your registers to provide a comfort in a building. The same thing is true with ductless. Is you still have to place the indoor equipment in the space somewhere. You have to decide how to do that, and there's guidelines for that. You know, I think one of the challenges you have with ductless is, and you'll see examples, I think if you look out there, is that they have to find other means to distribute that capacity once you get to a local zone if you have multiple small rooms. But there's solutions out there. You just have to go look for them. And so it may be being kind of proactive and identifying, you know, I think this is going to be a challenge and I need to go ahead and identify a solution, right?
Great, thank you so much, Wayne. And Matt, I see that you're setting up. So Wayne, we're going to ask you one more question while we let Matt set up. And this question is, how common is occupancy detection and occupancy dependent HVAC control in the residential sector?
So in residential, I would say it's less common. Now, when I say less common, it doesn't mean it's not available. I would just say that I would not say that most people are using it. So I know that many people, through their thermostat controls, many people have remote access capabilities. Part of that remote access is abilities to do occupancy detection, and those features are available. And so the technology is out there. But I don't know, you know, it's like as you introduce a new technology, you have to get market acceptance. People have to start using it. And I would say as we're at the point as an industry that the solutions are there, but it's probably not the point where it's been adopted on a large scale.
All right. Thank you, Wayne, for filling in for me.
No
I apologize for the technical difficulties here. Something obviously wasn't agreeing with my system, so I had to reboot. But we're back on track here. So as Wayne alluded to, My area of discussion here this afternoon is going to be talking a little bit more about that load sizing element, as well as doing energy analysis and helping you through enabling you to understand a tool that we have available to you to do the analysis yourself. And so we're going to talk a little bit about building systems or building energy modeling. But before we do that, I want to get into kind of some very low-level understanding in general about what building modeling is and how it's used within the industry before we get into the direct product and going through a demonstration with the product. So we're going to talk about the modeling. We're going to talk about how it's used in the industry. I'll talk a little bit about what the presence of and the product itself, its past history, and then we'll go in and show you the new product that we released in September of 2017. So what is building modeling? And building modeling can be used for all sorts of things. Basically, what we're talking about here is creating a virtual physics-based replica of a building or a series of buildings. There's urban modeling. There's load design specific modeling where you're just trying to get the HVAC sizing. And then there's energy and economic analysis. And fortunately, the tool we're going to show you today combines all those capabilities. It's used for comparative and predictive design and analysis. From the past, the physics-based modeling and the power of the computing platform that it's used on really dictated whether you could use it for comparative or predictive analysis. And as we see today, computers are getting more and more powerful, and the industry is moving more towards predictive analysis, although comparative analysis is used regularly. Basically, what we're talking about here is taking all those elements, several of which Wayne talked about, and pulling them together, defining them at a little bit deeper level, and then allowing an engine to consume all those pieces of information from the weather, like Wayne talked about with the design conditions and the actual typical weather profile for a location, the construction, is it brick, is there gypsum, is there insulation, and how many inches of insulation might be and what type of insulation, the computers, the lights that are in the space, the people's interaction with that airflow and the temperature in the space, and then the components and the layout that Wayne talked about for many of those different elements, looking at variations of different layouts and options. And as you get into the commercial side of the world, there's many, many more options than even what Wayne had showed you, which really was more on the light commercial or residential side. And then in the end, you want to take the cost elements because that's driving a lot of the decision making on the investments, whether you're looking at the first cost of the building, then that's really important to the owner, or if you're looking at the life cycle cost of the building and then taking those parameters and figuring out what the best solution is. So we throw that into an engine, and what we're going to be talking about for an engine is the Energy Plus engine that's been developed since 1995. We take the operating parameters and some simulation parameters to tell them what's important to us in that process, and we let it run through that engine and then spit out a series of results. The results can give us the equipment sizing information, it can give us operational results, and it can give us that financial impact. So all those different pieces come together. So how is it used in the modeling industry? Interestingly enough, this can be used at any point in the building life cycle. Oftentimes it's used early in the planning stages or the conceptual design, and for certain when you get into design development and you're starting to do some very detailed design elements of it. But interestingly enough, it could also be used all the way over into the operations and support of the building. In other words, we can go in and we can look at a facility's operation from the actual utility bills. We can optimize the model to match the utility bills, and then we might be able to predict when we add energy saving measures to a building what they might do given that optimization or calibration that's been completed. So the owner will say, I want this or that investigator, or I have this much investment available. The architect then pulls the elements associated with the physical layout of the building at a high level, and then the details for the HVAC system are determined by the engineer, and they might be, any one of these might be using this software to kind of give some payback or some justification for ideas they have related to the building. In the end, what you see here in the lower right is just a discussion about building energy modeling, that's BEM, has all different parts and pieces, whether it's code compliance or wanting to look at utility rebates or wanting to look at environmental impacts, life cycle cost analysis, or if a manufacturer is doing research and development to try to figure things out. all these pieces come together in the building modeling world. From a history perspective, we have a product called Trace. It's a long-standing product that's been out there since the early 1970s. Started in the punch card days where customers would literally send in punch cards of information. We would run them through mainframes and then get them back the results. Then it moved into the desktop environment in the 80s. And two of the current platforms we have, one is Trace 700, which is what you see there in the 1990s. Kind of a early Windows format feel to it. A lot of information, not as much visual information. But when we talk about today's product, we've kind of taken the next step and we've moved into the 3D realm, with thus the 3D name. So the product that we released in September is called Trace 3D Plus. It's moved away from a proprietary engine that we developed over that 45 years into this Energy Plus calculation engine. Gives us a little bit more flexibility and capability, especially when it comes to renewables, as well as some other sophisticated shading and solar aspects of that. 3D building design, obviously you're working with a full 3D model and not working with something where you might be putting in dimensions and not really being able to visualize what your building looks like, or if you made mistakes along the way. And then of course a lot of other visual aspects with configurable systems and plants, and I'll talk about that in a little bit more detail as we move into the application. So I have Trace 3D Plus here open. This is a product that's been updated into the Windows 8, Windows 10 kind of tile formatting that you see here. On the left-hand side, you're going to see projects, recent project lists that you've got, the ability to open a project or to create a new project. In the middle section here, you see the building elements. These are all the component elements that make up a building in various forms and feature sets. So these are the building blocks by which we're going to do the analysis. And so the libraries are, they're part and parcel to your model. You can work at them at a high level and create your own custom libraries for everything you can think of in terms of constructions, for instance. If you've got something that's, you want to work with a specific glass, or if you want to work with a specific door or a specific wall or a specific roof. Other libraries from that perspective go to the plant configurations, the equipment itself, the lights, the people, the miscellaneous loads in the space. And so those are all the foundational elements of the application. I'm not going to go into detail on that. We don't have a ton of time here. Really what I want to do is get back to showing you how this product can help you on your design projects. The other element here on the right-hand side is there's some news and updates information. There is some documentation available for various systems. So one of the ductless systems that Wayne had talked about was variable refrigerant flow systems. So there's a modeling guide for how to do that, and there's frequently asked questions on what to do, tips and tricks, etc. That'll bring you out to our support portal that has a lot of information readily available to help yourselves if you have any questions about the product. And then the last piece here on this desktop that I wanted to talk about was this what we call user preferences area. This is kind of the look and feel of the application. If you decided that you wanted to go with a specific interface or regional settings, for instance, the units and inch pounds, you can switch those over in this area of the application. And all you need to do is just click off in a typical Windows file kind of flyout format. So let me step into kind of the meat of the application, creating a new project. And you can see here that I have a bunch of recent ones. I'll open one up in a minute to show you kind of the output. But to show you kind of the ease and how the program is set up to walk you through this process, because as Wayne pointed out, as the buildings, small residential buildings, the load calculations are complicated enough. But as you move into large, complex facilities, schools, hospitals, those kind of facilities, you really do need a tool that can help direct you and walk you through this process. And that's exactly what this tool is designed to do. So if I just type in here the name of the product, I can change the image that I've got. And then I set some defaults about if this is the location that I would typically utilize. Am I going to simulate for load design to do the sizing of the HVAC, or am I going to do energy and economics, which would combine both? And then the time step, we can go from a 60-minute time step all the way down to a 1-minute time step. I wouldn't recommend that because obviously as the time steps increase, the calculation time to do that simulation and the complexity of the output, they grow as well in that process. Other inputs here are some physical parameters of the building that may change at different floors or different areas, but typically there's a common footprint for the floor-to-floor height, the ceiling elevation, the thickness of the walls, etc. So I'm just going to leave those for default for now. The next step in the process is we ask you what type of building. The Trace 700 platform, the predecessor to this product, actually you had to build all these from scratch on your own and then save them. We actually created several different building types here that you can utilize, and those libraries that are built within the application, there's tens of thousands of them. And so if you look here at, for instance, an outpatient healthcare facility, you'll see a bunch of room types. With every one of these room types, there's hundreds of variables and individual libraries that have been constructed to help model that particular space type for both load design as well as energy or economic analysis. So in this case, I'm just going to pick a low-rise office. I know that there's some schools and there are some multifamily residential buildings as well here. So we've got some templates that would match those types of facilities. I'm going to go ahead and create this project. Now, this takes a little bit of time because it's taking all of those libraries, moving them into the project file itself, and you're ready to move on with that theme that you've selected along the way. And then you can mix and match objects. So if you have a multi-use building, you could go in, for instance, and say, I've got a hotel, but it might have some retail space associated with it or office space associated with it. So you can mix and match the different templates that you see here. One of the other nice things about this is as you construct your building, you interact with those room types and the templates that have been that are part of that theme. So if I, for instance, have selected a low-rise office space, I might have an enclosed or an open office space. I can switch between the different components that are within that right from my project. I don't have to go back to the library and grab additional information. So the first thing you're going to see that when we come in here is a navigation bar across the top. This is a primary navigation bar that's going to lead you through the process. And again, the whole point here is we want to be able to analyze the building for load design calculations to size the HVAC correctly. We can account for both the sensible and the humidity, as Wayne had pointed out. It's so important to look at both pieces of that. And we can select different weather locations wherever we want around the world. There's about 3,300 weather locations already pre-built into the application, and it has kind of a Google look and feel. If you're connected to the internet, as you zoom out, you're going to see other weather locations that are available for you to select from. And then you can change the design parameters associated with those by going to the properties of the weather location that you're looking at. In this case, we've got La Crosse, Wisconsin, which is where I'm located. And you could change the design parameters per some of the documentation that Wayne pointed out earlier if you want to change those. I'm going to leave the weather location the way it is, talk a little bit more about how we construct the building in the program, because this is one of the cooler aspects in moving from our previous platform that wasn't visual in nature. And so we use a pretty sophisticated gaming engine in this process, and this allows us to take the Energy Plus 3D coordinate system that it's using for its modeling and turn it into a quick and easy to see visualization of the building that's fully rendered as you're drawing it. So in this case, I'm going to go in and I'm going to pick a floor plan that I've got, and I'm just going to pick a simple one here, a small office space. And then I'm going to go in here, set the origin location for the model, because that's the first thing it kind of wants me to do. And then I'm going to scale the drawing. Typically, you'd use a dimensional drawing, a leader or something off of the drawing to do that dimensioning. You don't have to. I just know the dimension in this particular case for this example. So this is about 57 feet, and I'm not worried about being very specific with this layout. Now it's a matter of kind of dragging and drawing over top of the existing system. So I just selected the rectangular drawing tool from the top menu, pretty self-explanatory. Again, I'm not worried about matching the dimensions exactly in this particular case, but I could just zoom in if I wanted to. And what you'll see on the left-hand side in the tree, as I construct this, it's actually constructing the 3D element of this on the fly. So if I open this room, you can see that I've got walls associated with it, highlights the space, and it gets the roof. It shows you the common wall with the italics and the walls that are there. So really easy to use, very quick. and all of the pre-built-in elements for you to do both that sizing analysis and the energy and economic analysis on your projects. So this is pretty cool. It doesn't take a ton of, I'll say, background training or material, although we have a fair amount of training material on the website. I'll show you a little bit later. There's also a lot of drawing tools down here, just like your CAD tools or packages that are out there. These are called snaps in the lower right that allow you to turn things on to snap to wall projections or perpendicular or parallel or to the grid. There are things to show, display things. If you want to show the exterior, interior dimensions like I'm showing here, if you want to show the room name or the room area, and then there are elements for visibility if you want to turn the walls off, if you want to turn the ceilings off so you can see other elements within your drawing. So pretty cool stuff along the way. I'm going to move over to what this is called the polyline drawing tool. I can go through the process of, again, enclosing spaces like you see here for odd-shaped spaces, or I can draw them and it'll continue to stay connected in a polyline shape until I enclose it. And then if I quickly switch over down on the lower left, you'll see a level view as well as a full building view. So if I click over to that, now I can see the construction for that building on this particular level. I can add additional levels using the buttons on the right-hand side. And again, I see the visualization of just the structure. The nice thing about this is that all of the room types and the template data that I've created is quickly assignable, and I'll show you that in just a second. But adding windows, for instance, or doors, really straightforward. Again, I click the window button, I zoom in, I can set the size for the windows that I might have, and then I can place those, and I'm not matching these up with this particular drawing. I'm just, for speed purposes, kind of going through and throwing some windows on here. And then from a doors perspective, again, I'm just going to throw a couple doors on quickly, this process. And now you can see again, I got a window that went into my tree on the left-hand side, and I can see the properties of those individual rooms by using the properties button here. But if I go over to the 3D view, again, those elements that I just added, they are now on the facility. So really straightforward and easy to use from that perspective. And again, from a room types perspective, all that template data that we selected for this low-rise office, I can quickly go in and change the types. You can see by default, it assigned all of the space to open office. Every theme gets a default room type, but I may want to change that to other space types. So in this case, I say this is enclosed office spaces. And I can say that this is restroom area here. And I can say that this is conference room area here, and you get the picture. So the other element to this is that the other segments of the application also utilize the 2D and 3D drawing elements as we continue to move through the process. So Wayne talked a little bit about zones and the idea behind zones. Really, these are thermally dissimilar spaces that you might want to create different terminal devices if there is a terminal level unit, or if this is a whole office building system, you may end up having one zone, and the whole building is one zone, and then you have kind of mixed conditions across all those zones. So I'm just going to add a couple of zones here and say, well, if I had a variable volume system for this small office, I might have a terminal that conditions this because this is the southwest facing of the building, which is going to get different solar profile and different loads based on its location and its space usage, versus the conference room up here that's in the northwest portion of the building. And so that's really what you have to look at when you look at a building's thermal properties, is what's common for the space types from a usage perspective, but also from a facing perspective from the sun that's going to drive solar loads from coming through the windows, and the airflow requirements to those spaces as well. I'm going to then move over here to the system section. There's a Create site where you can go in and literally place parking lot lights, PV, wind power as well. I'm going to skip over that for now, just in the essence of saving some time, and talk a little bit about systems. And when we talk about systems, these are the elements that Wayne had referenced with respect to those combinations of the condenser, compressor. Is it going to be chilled water or variable refrigerant flow? Are we going to have a unitary or what we call a direct expansion refrigerant system, just rooftop on top of the building? And so some of this terminology can get a little bit overwhelming, especially if you're new to this industry. From a commercial perspective, it's a little different from the residential perspective. You can see up here we've got terminology with some acronyms. So VAV, variable air volume with reheat. We've got radiant systems. We've got changeover bypass. And I've got the categories at the top. So if I had, for instance, a heating only system, I could click up here and I would get a different menu of items, a sub-menu of items here. If I've got a constant volume system where I've got an air handler that's just blowing air and I'm not varying the fan speed or airflow to the space, I can click on that and get a different menu. And so these kind of drill down. So in this case, if I look at a variable air volume system, the default here would be, for instance, a variable air volume system with a terminal device that modulates the airflow to the space. Disk direct expansion, not chilled water in the coil itself. So if I click on that, you can see the schematic layout that it provides you. These boxes down here in gray are the controllers. So there's a thermostat controller here, temperature controller. There's a thermostat, there's a relative humidity sensor here at this location connected to this controller, and both of those controllers are connected to the coils. The cool thing about Trace is that it's intelligent to know where you can place objects, where you can't, and it'll also tell you if you've messed up some of your configurations. So if you're new to this process, that's really, really handy because there's almost an infinite number of configurations that you could come up with. And we try to guide you to what we know the engine's capabilities are, as well as our applied knowledge that we've inserted within the application. So here you can see I've added that system now, and if I decide that I want to go in and configure that system, I can go in and add additional components. For instance, if I add a return fan, it's going to tell me that location is available. That's a constant volume return fan. If I put a variable frequency drive on that fan, now I can get different locations for that fan. And so the pre-configured systems, for those of you that are working in the project, is probably what you're going to want to utilize. You probably want to understand some of those energy conservation measures at a low level, and at any time you can hit F1 in the help, and it will then help you understand, in this case, the contextual nature of where you're at within the application and give you background information on utilizing some of those systems that you might want to analyze. You'll also notice things gray out. So as I've added components, other components have grayed out. And there is like I said, a validation thing that'll tell me, did I connect things up properly? Did I mess anything up in the process from a validation perspective at the bottom? This is very similar on the chill water plant side of things. I'm not going to go into that again, just in the essence of time. But from an assigning zones perspective, once we've configured the systems, those previous zones we created in the building, it's going to want to know what's connected to that HVAC system. So I come in here and use the visual aspects of that to assign those systems. And then if I want to get into the details of specific zones and change the specific zones themselves, I can go into configure zone equipment and go into more detail. Again, from the plant side, it's very similar to the HVAC side, system side. This is dealing with, if you have a VRF system, you'll have a plant for the refrigerant side to connect up all of the terminal devices. If you have a chill water side system, you're going to need a plant as well. This is where you would do that, as well as the ground source heat pump system. So if I go in here and say, for instance, select plant, I can select chill water loops, hot water loops, condenser water loops, and I can use this plant wizard to pick, for instance, water-cooled plants that are already pre-configured for me. So if I've got what we call a chiller that's going to chill the water, we got a boiler, it's going to heat the water loop, and then we've got a heat rejection device that's going to take the heat from the chiller that is rejected from the building and you reject that to the atmosphere through what we call a cooling tower. So I can add that plant configuration to this system. And then if I move over to the economics side of the house here, this is where I would go in to the library, create a utility rate structure. We have some flat rates already here. Utilities often go off of dollars per kWh for the consumption, how much energy you're using over time, versus how much demand you're putting on their equipment at any one moment in time, which is the demand segment down here in dollars per kW. There's also, you can add natural gas, et cetera. So for every utility that you have within your building that's identified, the program, if you have that, will automatically assign it to the appropriate utilities, and you can reassign that as you see fit. You can also enter in here life cycle cost parameters associated with if you're going to do a life cycle analysis. So in here you got 25-year study, what's your discount rate, what's your utility escalation factors, and then from a cost perspective, you could put in your first costs as well as maintenance costs associated with your projects. And when you're done, you're going to come to this project summary screen. It's going to show you a single alternative that's been created. Now here you can see I've not completed my analysis. It's giving me some signals that says you have something missing. You have zones created that you have not assigned in your building. You either have to say those are unconditioned or do something else with them. And that's the kind of help the program's going to give you throughout. You can also copy your alternative and start to make modifications of that. That's when you start to look at the different variations or energy conservation measures that you might want to analyze in your facility. When you're done with all your alternatives, putting that together, you'd come over to the calculation results screen, select which alternatives you'd like to run, and then once it's done running, you would go into the reports or the visualization to analyze your results even further. There's also simulation settings here that allow you to adjust specific measures within your analysis. But from a high level, the whole idea is we want to be able to size the HVAC system, we want to be able to analyze different alternatives, and we want to be able to do energy or economic analysis depending on what the objective of the end user is. So I know I went through that very fast. There's lots of material out there to help any of you that are interested in utilizing this product and the project. First and foremost, I'll go out there and talk a little bit about some of the free training materials. So if you go to train.com and visit the commercial website, you can get to the training materials from the training tab at the top here, and then you'll see design and analysis software. There's also educational resources on top of what Wayne provided there in the training menu as well that you might want to look at that could help you on the projects. And then on the e-learning side of the house here, this is where you'll see e-learning courses. So there's descriptions of what the courses are that are available here, and then go to the e-learning courses to actually do this. And there's 2 hours of videos, one for load design, for sizing HVAC equipment, and then another hour of doing energy and economic analysis out there and available. So that's the 3D Plus tutorial videos. There is also a fair amount of online material that I talked about just in the inside menu and the F1 help that can get you started along with that process. And of course, if you have questions and you're working through your projects, if you work through your professors to contact our support center, we can also help you through that means as well. If you're interested in getting the application, there's 2 different ways that you can go about it. An email should have been sent to your schools that gave directions on how to get a license through the sponsorship opportunities that we have available. If you want to just evaluate it to see if it's something you want to use, we have a full trial version, 30 days. It has full functionality within the application. You can go to our download center back here on the website that we've got. Sorry, I got to go back to the top menu here and go into the actual systems and sizing that we've got. So design and analysis tools menu at the top here, and if you go into our download center, this is where you would then access any trial software that we have for the product. So I'll open it up at this point to any questions. I know Wayne already answered quite a few questions.
Great. Thank you, Matt. This was fantastic to see all this information. We're going to wrap up as we're almost done, and people can contact the organizers, and we will be happy to send any of your questions on to either of the presenters today. So in conclusion, I know you all are working really hard on your projects. If there's some excitement you want to share, please use the hashtag Solar Decathlon Design. We look forward to seeing your team's progress, and that's one of the great ways we can see that. Thank you again to our sponsors, Ingersoll Rand and Solar Edge are our host sponsors. We also do have a variety of education sponsors, and if you're interested in learning more about them, you can hear the sponsor webinars on the groups.io page as well. And Solar Edge actually will be giving a webinar in a few weeks. Do note that all of these webinars are on the groups.io, are recorded and posted there with a PDF of the slides. So our next webinar will be on February 6th at 3 p.m. Eastern. You can register today, and this will be the organizer staff talking about how to prepare your project progress report. So don't miss it. There will be a lot of useful competition information available in there. So with that, we will close. Feel free to send us any of your questions. You can reach us solardecathlon@nrel.gov or sddesign@nrel.gov if it's particularly for Design Challenge. Thank you again to Wayne and Matt. You were fantastic speakers, and have a great day.